A military jet pushes the envelope of innovation, but at a deadly cost. A North Sea oil platform is devoured by flames in minutes. The worst construction accident in U.S. history takes seconds. A deluxe high-speed train derails, and computer errors nearly cause the unthinkable. Now, engineering disasters on Modern Marvels. It was a startling leap forward in aviation. An airplane that could rise from a standstill, hover, fly like a conventional jet, and then land on a dime.
When a plane that big comes straight down and lands right in front of you, it's very impressive.
The Harrier AV-8 attack jet, an aircraft flown and maintained by the U.S. Marine Corps Aviation Wing. Its unique feat of engineering and piloting is called VSTOL, vertical and short takeoff and landing. It's meant to support Marine ground troops deep in the combat zone, where runways might be damaged or non-existent. But the plane's VSTOL capability has come at a terrible price.
Measured by its major accident rate per 100,000 flight hours, which is the military standard, the Harrier is the most dangerous plane in the U.S. military. Overall, the Marines have lost more than 1/3 of the entire Harrier fleet to accidents.
148 major non-combat accidents in its 30-plus years of service. Billions spent on repairs alone. Worst of all, 45 Marines, including some of the Corps' finest aviators, killed during peacetime.
In Marine Corps aviation, I don't know of another aircraft that took the toll of time, money, and lives to perfect its operation.
Unlike most engineering disasters, the Harrier's failures did not occur in a single catastrophic event, but rather over the fleet's long lifetime. And while the Marine Corps has stuck by the Harrier for over 30 years, the need for an airplane like it can be traced as far back as 1942 and the fierce jungle combat on Guadalcanal,
where the Marines felt that the Navy left them to battle the Japanese and malaria and lost 1,000 men in that combat. Since then, the precept that the Marines in the air should protect Marines on the ground has been a central part of the Corps' ethos.
The Marines continued to fight some of the fiercest battles in U.S. history. And they continued their search for an attack plane that could provide close air support in the worst of conditions. Flown by Marines and for Marines. In the 1960s, they thought they'd finally found it in an experimental British aircraft called the P-1127, soon to be renamed the Harrier, after a bird of prey.
So when the British developed the Harrier, the Marines were immediately interested, and in fact, one Marine general who flew the plane early on described it as an answer to a prayer.
In 1970, the Marines placed a large order for the jets with the British manufacturer, Hawker Siddeley. By May 1971, active Marine units began flying the Harrier, now called the AV-8A.
The AV-8A was a notoriously unstable plane which had a tendency to roll over and slam into the ground. It had an astronomical major accident rate.
1 month after being rushed into duty, the first fatal crash occurred. Collapsing landing gear, fuel tank malfunctions, and jammed control sticks were among the causes of fatal crashes. In addition to malfunctioning equipment, the AV-8A presented steep challenges for pilots. While manning the control stick, rudder pedals, and throttle, a Harrier pilot also had to learn to control the 4 nozzles that provide the thrust for vertical flight, all while keeping an eye on the wind.
There's no doubt that under the best of circumstances, the Harrier is a challenging plane to fly.
I am always very skeptical when the U.S. military blames something on pilot error. Far too often that's not the real cause. The real cause is in the design. And if the design is a very difficult design to work with, no amount of training can overcome those weaknesses.
The AV-8A was also frustrating for mechanics.
When it came to the heavy maintenance, we found ourselves short in special tools and the special slings and adapters, measuring devices for that aircraft. We just didn't have it. Early on was a disaster.
The AV-8A's difficult design and persistent mechanical flaws contributed to a disastrous first decade, with annual accident rates as high as 57 per 100,000 flight hours. By comparison, the FA-18, while a more conventional aircraft, had an accident rate of only 8 per 100,000 hours in its worst year. In the early 1980s, the Marine Corps introduced the retooled Harrier AV-8B. Its larger wing was designed to provide better stability in flight. Greater engine air intake and a new avionics suite to improve navigation were also added.
The accident rate for the AV-8B has been considerably lower than the AV-8A, but it remains far higher than the comparable contemporary attack and fighter jets flown by the Navy, Air Force, and Marines. The AV-8B was first introduced to the fleet in the mid-1980s, and by 1996, nearly a quarter of them have been destroyed in accidents.
Half of the Harrier's 148 major accidents have been connected to problems with its powerful but temperamental Rolls-Royce vectored thrust engine. Repairs and maintenance are complicated by the fact that the Harrier's engine is exceedingly difficult to access.
To do a full engine change-out on a Harrier can be over 500 hours of labor, whereas in other military jets it can be a day or a half a day, part of a day, to do the same thing.
The Harrier's frequent groundings and time-intensive repairs have created a catch-22 for many pilots. They can't log enough flying hours to stay sharp, which leads to more accidents, which leads to even less flying time.
In 1997, they brought back a former training squadron commander, and he found that some of these pilots, inexperienced pilots, were getting only 4 or 5 hours a month, which he said was not enough to fly a Cessna, never mind a Harrier.
Renewed scrutiny has focused on the Harrier's record in combat. In the 1991 Gulf War, the Harrier flew over 3,300 missions, but also sustained the highest casualty rate of major U.S. combat jets. 5 of the 7 AV-8Bs that took enemy fire were destroyed. The Harrier's attrition rate was 3 times that of the A-10 attack jet and 7 times that of the F-16. Again, what made the Harrier special also made it vulnerable.
Infrared seeking missiles will see the big engine from the Harrier. It is very hot, and so surface-to-air missiles with infrared seekers on them will go right for that engine.
During Operation Iraqi Freedom, the Harrier, now outfitted with laser-guided weapons that allowed it to attack from higher altitudes, performed admirably. None were shot down, but a nagging question remained. Was the Harrier necessary?
What we saw in Afghanistan and in the war in Iraq was airstrikes conducted from great distances with precision-guided bombs and missiles. So I think a lot of the use that the Harrier got in Afghanistan and Iraq was sort of giving it a fair chance to show what it could do, but you'd be hard-pressed to show that we couldn't have done the same things other ways.
While Congress, prompted in part by a series of articles in the Los Angeles Times, investigates the Harrier's latest spike in crashes, the future of marine aviation is focused on the plane that will one day replace the Harrier, the Joint Strike Fighter. The Marines' model of the JSF, although it won't have the Harrier's distinctive V-STOL ability, will have short takeoff and vertical landing capability. And it will be outfitted with advanced flight control software to take some of the burden from pilots. An airplane that matches the Marines' mission to fight anywhere, anytime, and get out alive. The Marines hope the JSF will surpass the performance of the Harrier, without the same toll in money, material, and most importantly, lives.
The Harrier is still flown by the British Royal Air Force and Navy, and is also used in Spain, Italy, India, and Thailand.
We now return to engineering disasters on Modern Marvels. July 6, 1988 was a clear, calm night on the often tumultuous North Sea. But the calm would be shattered by an engineering disaster of mythic proportions. A hydrocarbon-fueled inferno that would become synonymous with the worst-case scenario for an offshore oil platform. The platform's name was Piper Alpha.
The magnitude of this disaster was a significant event in human history, and indeed, the history of the North Sea after it will be forever different because of its occurrence.
It was also the greatest loss of lives on an oil or gas platform. 167 men perished, victims of a tragic confluence of design flaw, human error, and bad luck. Oil was discovered under the cold, rough North Sea in 1969. Occidental Petroleum, one of the first companies to claim the North Sea fields, knew that to succeed, it would have to think big. The result was the Piper Alpha.
This was the first platform of this type and scale in the North Sea. It cost $1 billion in 1975 dollars. So this was a significant engineering platform. The challenges of building a whole processing refinery that sits on the seabed of the North Sea is particularly challenging.
It weighed 30,000 tons. Its lowest level rose 84 feet above the water to account for the North Sea's giant waves. The Piper was a mini-city, home to over 200 men who lived and worked on the platform for weeks at a time. 35 gas and oil wells fed into separation modules. A maze of pipes, tanks, pumps, and valves, which separated the oil from the natural gas and water. The oil was shipped to shore in a 128-mile pipeline. Processing the gas was more complicated.
The gas that came out of the formation under the Piper Alpha wasn't just methane, which is a very light hydrocarbon gas. It also contained propane, pentane, which are heavy hydrocarbon gases.
The lighter gas was sent to processing platforms connected to the Piper. The heavier gases were condensed into liquid by applying high pressure and low temperatures. The liquid gas, or condensate, was then piped to shore, conveniently alongside the oil. Keeping the heavy gases in liquid form required the use of powerful pressurizers, called condensate pumps. On July 6, 1988, a failed valve on a condensate pump would trigger a disaster of extraordinary scale. It began with routine maintenance.
There were several hundred valves on the platform. Each of these had to be checked at least once every 18 months, according to their technical safety requirements. One of the valves on one of the condensate pumps was off for recertification.
While the valve on condensate line A was down for repairs, the redundant line B remained active. But there was a problem with line B. Hydrates were forming at a high rate.
Hydrate, which occurs in processing oil coming out of the ground, is nothing more than ice with a little hydrocarbon in it. However, if you think ice is an irritant in your house plumbing, you ought to see it form in a hydroprocessing line. It can totally stop the process.
The methanol injection system, which essentially puts antifreeze into the line, had failed. Line B shut down automatically.
This is very bad. First of all, it has grave economic consequences, but if you have to shut the platform down and go from what they call a black start, that means bring everything start from cold, that is a real headache.
It was necessary to find something to do real quick to either get that pump back in service or to start the other pump. So they sent an electrician down to check the instrumentation. This particular safety valve was in an awkward position because it was located well above the pump that it protected. He could not see the safety valve from the position where he worked on the pump. He went back up and said that it was okay.
Due to the pump's design and a lack of communication, the night crew didn't realize the extent to which Line A had been disabled. When the Line A pump was repressurized, gas at 1100 psi shot out of the valve with a deafening shriek.
So eventually, this layer of condensate gas, which now, of course, has become mixed with oxygen and is only looking for an ignition source, finds the ignition source.
What that source was may never be known. But at 10 o'clock, a giant fireball ripped through the condenser module and destroyed the control room.
The initial explosion, if that's all that would have happened, we probably would have been okay. But unfortunately, the initial explosion appears to have fractured the main oil line in the B module.
And that contributed a large amount of fuel to the fire. Crude oil happens to burn with a very thick black smoke, and that dense smoke basically rendered that entire deck uninhabitable very quickly.
With the smoke making helicopter evacuation impossible, workers trapped above the burning production module had no good way to escape.
So you've got to find your way in dense, dark clouds of black smoke in the middle of the night, find a rope, and crawl 10 stories down and drop into 40-degree water and survive.
The oil fire grew so hot that a major gas pipeline exploded. The Piper Alpha's unmatched ability to collect and process prodigious amounts of hydrocarbon fuel now led to its rapid demise.
These pressurized pipelines represent huge fuel sources that, when they come back, literally melt the 30,000 tons of the Piper right to the waterline.
Of the 226 people aboard the Piper Alpha, only 61 survived. 165 workers and 2 rescuers died. The financial impact on Britain's oil industry was staggering.
The Piper Alpha disaster still, I believe, retains the title of the most expensive man-made disaster in history. The year before the Piper Alpha disaster, I believe the British government took in 12.5 billion pounds in oil taxation revenue, and in 88, 89, it was only 3.6 billion.
After tracing the source of the fire to the failed valve, engineers focused on how the Piper's design flaws may have contributed to the fire's extreme severity. Among the failures, inadequate blast walls protecting the control room, the lack of alternative ways to shut off gas lines or activate fire suppression pumps, and insufficient exits for the workers.
Once you called an emergency and you mustered everybody in the living quarters, there was no way for people to get out of there. In the new designs, they actually have shielded stairwells and tunnels and pathways where there's multiple ways out of the living quarters to get you down to a safe refuge and to your lifeboat stations.
This engineering disaster forever changed the way offshore platforms operate. For those who design and work on these mighty structures, there is no more potent reminder of what can go wrong than the name Piper Alpha.
The UK's annual natural gas production, mostly from North Sea wells, is greater than that of any Middle Eastern nation. This modern...
We now return to engineering disasters on Modern Marvels. Just off Highway 2 in Willow Island, West Virginia, a stone's throw from the muddy Ohio River, stands a simple monument. Upon closer inspection, it is a somber memorial.
The memorial was made out of concrete going up into the shape of a cooling tower, and it has a bronze plaque on the front of it with the 51 names, and then it has a verse on the front.
Anthony Lauer, beginning at age 12, spearheaded the fundraising efforts to build the memorial. 9 of his relatives, including his grandfather, are among the names on the plaque.
What I learned in doing the project was pretty much everything, because when I first started, no one ever talked about it around the house. Then I turned to the books, which the textbooks really didn't have much either. And then while doing the project, I learned what happened.
What happened on April 27, 1978, was the worst construction accident in U.S. history, and it happened less than a half-mile from here. This is the Pleasance Power Station in Willow Island, West Virginia. The power plant burns coal, heating water pumped from the Ohio River to create steam, which turns the electricity-generating turbines. Before returning to the plant, the water must be cooled in these tall concrete structures known as natural draft cooling towers. The identical towers are notable for their considerable size. 428 feet high, 359 feet wide at the base, and distinctive shape.
We call it the hyperbolic paraboloid shape, which, by the way, helps it generate natural draft. It is an extremely difficult structure to construct. One cannot construct this tower using normal methods.
In 1977, the contractor, Research Cottrell, decided to use its newly patented and highly complex lift system, called a jump form. It combined both scaffolding and the formwork into which concrete was poured.
It is a traveling scaffold that's literally climbing up the constructed portion of the tower.
Unlike traditional scaffolding, the jump form system was not anchored to the ground, only to the previously poured forms of the concrete shell. The most critical components of the system are these vertical jump form beams.
Those beams were bolted on both the outside face as well as the inside face of the concrete shell, so that the whole assembly of scaffold on the outside and the inside would ride, so to speak, on those beams.
To move the system up, workers unbolted the lowest beams, leapfrogged them to the top, and reattached them to the concrete shell. Then the entire system was jacked up by a hydraulic ram. As construction progressed, the cooling tower shell bore the weight of the scaffold, work platforms, and several dozen workers.
You had carpenters there moving the forming system up. You had iron workers there tying reinforcement bars. You had laborers there that were coming in behind actually pouring the concrete.
6 cathead cranes hoisting 3,000-pound buckets of concrete were also supported by the tower shell. Using this complex but effective method, the construction crew had successfully completed the first tower by August of 1977. Work on the second tower began in the spring of 1978, as soon as the weather was warm enough. The crew poured concrete in 5-foot-high sections called lifts. The goal was to pour 1 lift every day.
On April 27, 1978, they had constructed 28 lifts, and they were about to construct, or they had started actually, to construct lift number 29.
At 10 a.m., 51 workers were on the scaffold, which encircled the top of the tower 166 feet above the ground. As the day's third bucket of concrete neared the top, workers on the ground heard a loud, violent noise.
It was similar to like lightning striking right next to, you know, that horrendous crack.
The entire scaffold and construction system began to collapse as the top layer of concrete crumbled. Starting at the north end of the tower, the concrete and scaffold peeled off in both directions, detaching from the rim and falling inward.
I estimate that it was probably less than a minute, much less than a minute. Once it started going, its speed must have started actually increasing because of the added weight that was pulling down the rest of the scaffold.
It brought down all 51 men with it. Workers on the ground ran through the shroud of dust and into the tower.
Our first thought was to look for our fellow workers who were on that tower. Everyone was scrambling, looking for someone, you know, to see if there was anyone alive. And of course, in the end, there wasn't anyone.
Engineers from the National Bureau of Standards and from private firms arrived to sift through the wreckage and determine what had caused the deadliest construction accident on American soil. During lab tests on the disintegrated concrete from the 28th lift, the NBS made an important discovery.
We estimated that strength to be somewhere around 200 psi. Normally, for that construction, they should have had about 800 psi concrete. Concrete gains strength for two factors. One is the temperature condition. The other one is time. The temperature that night dipped down substantially low, so that the strength gain was much, much slower than the previous days.
There's little doubt that the partially cured concrete had not been strong enough to hold up the scaffold. But other analysts trace the main cause to a critical failure lower on the tower.
When we examined the beams themselves that were at the base of the tower, we found that the actual point where they had been connected, or they were supposed to have been connected, were intact and they were not deformed.
In other words, some of the lower bolts had not been connected to the concrete at all. The evidence suggested that the construction crew had prematurely unbolted the jump form beams from lift 27, where the cured concrete would have been of sufficient strength. The forensic engineers did agree on two very important points. One was the vital importance of properly engineered scaffolding. The failed scaffold at Pleasance Power Station brought this often overlooked problem to the foreground.
In fact, our investigation showed that it was not even an engineered structure. It was put together by some very sharp inventor that had some good practical knowledge, but nothing of systematic engineering to engineer a critical component like that.
The other point was the need for on-site testing of concrete strength.
So now the non-destructive testing procedure in some parts of the United States must be used to determine the strength of concrete prior to removing forms. As a result, I don't think that we haven't seen as many of construction failures in this country.
As for the Pleasance cooling tower, the job was completed 18 months later using traditional scaffolding. But it took many more years for the emotional scars to heal.
Since I got this done, I found that people are more open to talk about it now. Like, normally no one would talk about it, but now that it's complete, and it lets people know that it's okay. We can talk about it now.
In the end, the Pleasance cooling tower collapse resulted from the failure of two elements found at nearly every major construction site: concrete and scaffolding. The disaster was tragic proof that such elements, no matter how common, can never be taken for granted.
Each cooling tower at the Pleasance Power Station circulates 227,000 gallons of water per minute. This modern
4, 3, 2, 1, 0.
Humankind has been pushed to the brink of nuclear war on more than one occasion. And while the political reasons for these terrifying standoffs are well documented, lesser-known engineering and logistical failures have come closer to setting off World War III than one might believe. Satellite miscalculations, alarm failures, communication breakdowns, and even computer bugs have nearly brought on the ultimate engineering disaster. Some of these incidents can be traced as far back as the Cuban Missile Crisis.
The Cuban Missile Crisis was a seminal event, the most dangerous moment in human history. John Kennedy estimated at the time and afterwards that there was about a 1 in 3 chance that this confrontation would roll all the way to war, including nuclear war. The missile crisis is actually a wonderful case study for how many things can go wrong.
Radar glitches, faulty missile tests, and unauthorized U-2 spy missions were just some of the technical failures that heightened the already elevated chance of disaster. One especially surreal incident occurred on October 25, 1962, at the height of the crisis, when the sighting of a shadowy figure outside a military base in Minnesota triggered sabotage alarms at all nearby bases. At Volk Field in Wisconsin, instead of the sabotage alarm, the klaxon alarm ordering the launch of nuclear-armed aircraft rang out. A squadron of planes raced down the runway and were within seconds of taking off when the malfunction was recognized. The shadowy figure at the fence turned out to be a bear.
The Cuban Missile Crisis revealed a great deal of disorganization in the system used to manage the forces in a crisis. Keep in mind that this was a fairly young nuclear force. The missiles were just coming online.
After the Cuban Missile Crisis had been diffused, the United States worked to streamline its nuclear command and improve communications among the far-flung nodes of the nuclear network. But one of the results of improved readiness meant going on permanent hair-trigger alert.
We married the bombs up to the missiles and put them on basically 2 to 3 minute launch readiness.
Meanwhile, by the 1970s, the Soviet Union had built up a formidable arsenal of submarine-launched missiles, some of which could reach American cities in 12 minutes. Even more pressure was placed on the technologies, including computers used to help human beings make launch decisions. Sometimes these technologies failed. As the 1970s came to a close, computer errors twice brought us dangerously close to nuclear conflict with the Soviet Union. The first occurred on November 9th, 1979.
Out in Colorado at an Air Force base, a simulation of a full-scale Soviet attack in a tape was inserted into a piece of equipment to test the equipment. And someone forgot to flip the switch that kept that simulated attack contained within that one piece of equipment on the base. And in failing to flip that switch, the simulated Soviet attack was transmitted throughout the early warning network of the United States.
Top-ranking officers convened immediately to assess the threat. NORAD alerted its entire air interceptor force, and at least 10 planes went airborne. Under America's prairies, Minutemen launch silos prepared for attack.
Among the steps that we took to get ready for nuclear war, crews retrieved launch keys from their safes, as well as the launch codes that would be used to validate a launch order, strapped into their chairs to brace for an incoming strike and to be ready to fire their missiles in 2 minutes as soon as the order came down from the president.
In the ultimate sign that this threat was judged to be real, the National Emergency Airborne Command Post, or Doomsday Plane, also took off. It took 8 minutes, an eternity in the world of nuclear war, for the officers huddled inside Cheyenne Mountain to trust their early warning satellites and decide that the massive Soviet attack was not real. It was supposed to take them only 3 minutes. The incident, which was leaked to the press, so unnerved Soviet Premier Leonid Brezhnev that he personally wrote President Carter, urging improvements in the U.S. ability to recognize a false alert. Incredibly, 7 months later, another computer disaster would trick the U.S. into preparing its forces for nuclear war.
In 1980, the false alarm was triggered by the failure of a 43-cent computer chip that was part of a communications device that was used to transmit from our early warning center in Colorado to the rest of the nuclear forces.
The failed computer chip was in a device called a multiplexer, which transmits routine status information from NORAD's fortress at Cheyenne Mountain, Colorado, to the other command posts. The displays at the Pentagon and Strategic Air Command, or SAC, suddenly indicated a massive Soviet strike. This terrifying computer error looked real enough to once again order bombers to start their engines and silo officers to retrieve their launch keys and strap in.
So in 1980, the Cheyenne crew dropped the ball and failed for the second time in less than a year to come to the right conclusion that we were not under an attack in 3 minutes. It took them 8 minutes. The early warning crew at Cheyenne Mountain also was fired.
These disastrous incidents led to several key reforms in the nation's warning system. First, NORAD changed its computers so that officers in the mountain could actually see the messages they were sending to the Pentagon and SAC. In each incident, NORAD had no idea it was transmitting warnings of World War III. SAC's duty officers were ordered to check early warning satellites and radar before alerting the bomber force. And NORAD constructed a separate $16 million computer testing facility, so the training tape incident would never happen again. As sobering as our near misses have been, some defense analysts worry even more about our former Cold War adversary.
I would say that if we're making a list of worries in the nuclear arena, Russia's systems today should be a matter of considerable concern, because we all know about Russia's Mir space station. What happened to that? It failed. We all know about the Russian Kursk, their most advanced new nuclear submarine, which on its maiden voyage sank. We know about this recent event in which, at Putin's test of Russia's nuclear forces, they had 3 separate occasions on which they tried to fire a missile. In each one of the cases, it failed.
The concern lies not only with Russian early warning and control, which is deteriorating, but with our own, because command and control is inherently imperfect. The public has become complacent and doesn't even realize today that the United States and Russia continue to operate our early warning and nuclear forces, thousands of them, as though we had to be prepared to fight a large-scale nuclear war with each other at the drop of a hat.
Whatever solutions we find for reducing the chance of a nuclear disaster, our near disasters have made one thing clear. We cannot rely on technology alone.
In 1995, the test launch of a rocket in Norway appeared to Russian radar operators as a U.S. missile. The threat was taken so seriously that President Boris Yeltsin's laptop containing missile launch permission codes was activated for the first time.
We now return to engineering disasters on Modern Marvels. A train wreck. The essence of a well-ordered system reduced to chaos. The very phrase train wreck has come to mean any out-of-control disaster. And although rail travel is among the very safest ways to get around, when a passenger train traveling at high speed does crash, whether through derailment or collision, scores, even hundreds of passengers can die. In 1964, the world was introduced to high-speed rail with Japan's Shinkansen, or bullet train. The trains ran at a top speed of 133 miles per hour. Today, the bullet trains and France's TGV line carry passengers at speeds of up to 186 miles per hour. High-speed trains have proven to be a remarkably efficient means of transportation. And until 1998, they'd been remarkably safe. On June 3rd of that year, the violent crash of a German ICE high-speed train near the small town of Aschede highlighted the need for extremely precise engineering for these extremely fast trains.
The entire railroad community was shocked when the Aschede accident took place. It represented not only the first fatal accident on the ICE system, but essentially it was the first significant high-speed rail accident anywhere in the world.
The ICE, or Intercity Express trains, began service in Germany in 1991, and they were an instant hit. Germany had enjoyed a long love affair with speed thanks to the Autobahn. The ICE trains, which reach operating speeds of up to 175 miles per hour, increased German train ridership by 30%. The trains offered a smooth, comfortable ride, thanks in part to a new wheel design.
They have a piece of rubber in between the outer rim and the inner part of the wheel. And the purpose of that rubber is to lower the noise and the vibrations that the wheels cause.
We call it a resilient wheel. This is a very common practice used on light rail vehicles, streetcars, but this was the first application of such a wheel on a high-speed rail train.
The decision to use the resilient wheel design on the ICE train proved fateful. On the morning of June 3, 1998, ICE train 884 was traveling between Munich and Hamburg. The 2 power cars, one front and one rear, and 12 passenger cars, were speeding along at 112 miles per hour. About 5 minutes away from the Yashida station, passengers felt a sharp jolt, followed by jarring vibrations, which lasted about 2 minutes. On the first passenger car, the steel tire had peeled off from the core of the resilient wheel.
The tire actually fractured, came apart under the car, and hung up on part of the track brake. The wheel was carried along in this position down the track.
As the train approached a series of turnout switches on its way to the Yashida station, the broken tire struck the guide rail of the first turnout, causing the first two cars to lean sideways.
After that had happened, things began to go wrong very quickly.
With the concrete overpass coming up fast, the careening wheels of car number 1 damaged the switch points, meaning that any one of the following cars might be diverted to the turnout track. Passenger car number 3 was the first to switch to the turnout track, and the first to fly off the tracks completely. It smashed into the columns of the overpass.
If you think about the amount of energy that was associated with that collision, that train weighs more than two 747s, and then going at that speed.
The force of the collision brought the overpass down, crushing several train cars and causing the rest to pile up in accordion fashion. The degree of disintegration resembled a plane crash. 101 passengers were killed. Another 105 were injured, many of them critically. The damaged guide rail and switch points led investigators quickly to the broken wheel. Further analysis found that the inner layer of rubber had increased metal fatigue to the point where the inside of the steel rim cracked and separated.
Imagine if you had your bicycle and you put a steel band on the outside of the bicycle wheel. Every time that it rolled on the ground, that piece of metal will bend, and that bending causes stresses on the inside of the band.
But the flawed wheel design wasn't the only factor in this tragedy.
Usually to have an accident, and particularly to have a severe accident, it takes a combination of 2 or 3 events. I mean, in the case with the ICE, you needed the wheel to fail, you needed to go over a switch, and you needed to have a bridge all in the wrong place to create such a severe accident.
Nevertheless, 3 engineers involved in the wheel design faced 101 counts of negligent homicide in a German court. They were acquitted.
It's really a technical issue. What caused the flaw in the wheel probably initiated as a very tiny flaw inside of the metal part. It is extremely hard to detect those kinds of flaws.
After the Yashida disaster, ICE engineers reverted to the original all-steel monoblock wheel and installed a more advanced suspension system to reduce vibrations. Newer train cars were also built to absorb more energy, thus providing passengers with a better chance of survival in a crash.
One thing that really surprised me was the German engineer said that the Yashida accident would not be another Hindenburg. He said the Hindenburg accident basically finished the airship industry for Germany and the world, and that the German engineers were committed that this Yashida accident was not going to be a Hindenburg and prevent high-speed rail from being successful in Germany.
And indeed, the Yashida disaster did not dampen the German people's fondness for the ICE and high-speed rail. So how do we avoid what might be called the Hindenburg syndrome and actually benefit from an engineering disaster? It requires a careful analysis of what went wrong, as well as a bold, forward-looking redesign. And while lost human lives can never be recovered, the opportunity to learn and improve remains. Whether it's finishing the job or reinventing the wheel, engineers strive to perfect their designs and to find new and better ways to prevent disaster.
Next on History, a neighborhood is built around a canal. Years earlier,